build web applications without having to use any of the web technologies like JavaScript, CSS, HTML. The original was written in R, and it was designed as a way for data scientists who are already familiar with that language to be able to create web applications very easily while also utilizing the libraries that they're already comfortable with. This was what the original heat mapper was written in, but in 2022, Posit, the people who made Shiny, created PyShiny, which is the same fundamental idea, but rather than written in R, it is written in Python. So Python's brevity of syntax, the large amount of packages, and the popularity amongst general computing science makes it a very enticing offer to create web applications. At the same time, they also released ShinyLive, which is a method to use WebAssembly to change the original model of a server and client to strictly using WebAssembly on the client side, which can help improve performance. So first thing is, what is Python? Python is a high-level programming language that is touted as being very easy to learn. If you've ever taken a computer science class, this was probably the language that you used. But despite the simplicity, it's also very powerful. Its syntax is very concise, which means that you can do a lot with a few lines of code. And it's very popular, which means that its powerful standard library is expanded with a bunch of functionality, like matplotlib, which does plotting and graphs, pandas, which supports charts and tables, and numpy, which performs a lot of high-level mathematical functions. One of the main downsides that people claim is that Python is a lot slower than compiled languages like C. But to remedy this, there's a lot of libraries in Python specifically designed for speeding it up, such as Numba, which uses just-in-time compilation. And a lot of the popular libraries, like the aforementioned like NumPy and Matplotlib, aren't actually written in Python. They're written in a lower level C. And this will come important later on in the presentation. So the question is, why would we want to use PyShiny over RShiny? And the general advantages boil down to Python is generally faster, it's more concise, it uses less system resources, particularly memory for large data sets, which is often what we're using when we're creating data science applications. And its libraries of external applications are, if they either match or they exceed what R has, because R also has a lot of good libraries, but Python is close in that regard. So there's two big ideas behind Shiny's philosophy, which can be boiled down to efficiency and reactivity. So Shiny has its own reactivity engine, which handles the reactive components of your website. So pretty much every output, say something like a graph, is intrinsically linked to all of the inputs that were used to create it. So the file that was used, all of the settings that the user configures on the user interface. And Shiny will automatically manage this reactivity so that if any of the inputs that were used to create the output change, such as a slider or changing the file, Shiny automatically invalidates the output and asks for it to redraw it. So this makes it very easy to create an application with Shiny. You don't need to worry about managing the inputs and outputs. You just use the inputs when you need to use them, and Shiny handles updating the outputs in correspondence. Despite this simplicity on the surface, they also have support for reactive decorators. So you can explicitly say what inputs you want to invalidate an output. So for example, if you want to have an explicit update button, you can just tell the Shiny application that this output only gets redrawn when the update button is clicked, regardless of other inputs, which can help when you have large applications that are computationally expensive. Robustness is the second, which cuts both ways, not only because you have access to Python and its vast wealth of libraries, and Shiny can use all of those libraries seamlessly. Like you can use Matplotlib and NumPy as you would expect, and Shiny just handles the rendering. But because Shiny itself is written in Python, it can use very powerful web application libraries, which means while you can technically write the entire application in pure Python, you have the option of modifying the underlying HTML, CSS, and JavaScript when you need to. So the rest of this presentation is going to be kind of creating a PyShiny application, because the best way to learn is by doing. So the first step that we need to do is actually install Python. So Python can be installed from python.org. And once it's installed, we want to create this thing called a virtual environment. So Python will install itself as a system installation, but it's usually unwise to use the system installation for all of your separate projects because there can be conflicting dependencies and there can be a lot of clutter. So what usually you want to do is create a virtual environment, which is a copy of the system environment that is tailored to your application that you install the dependencies of that application into, that's isolated from your other applications. So it's very simple to install. All you need to do is open your shell of choice, like command prompt or terminal, and you just run Python, and then you specify the virtual environment module, and then a path that you want your new virtual environment to be in. Once that has been done, which only takes a couple seconds, you need to activate the virtual environment. This pretty much just tells your shell that rather than using the system Python, you want to use the virtual environments Python. This, again, is very simple. On Windows, you just run the activate.bat file, and on Mac and Linux, you just source the activate in the bin folder. Once you've done this, we can use Python's library manager, pip, to actually install Shiny. And it'll pull in all of the dependencies, and it'll put it in the virtual environment, and we can actually start using it. And to run Shiny, we run shiny run, and then we'll immediately get an error because we haven't actually created the application yet. So this here is the fundamental structure of a PyShiny application. There's 4 major parts, and here is a little more detail about each of them. So the first line is an import statement. So Python imports libraries using the import keyword. You can also use the from keyword if you only want to import specific parts of it. So in this case, we only want to import the app section of the Shiny library. This is the main coordinator that actually handles taking all of your data, opening the socket and listening to it, and handling all of the interaction. The second is the server. The server is all of the logic of your PyShiny application. So it includes all of the logic for generating the outputs, parsing the inputs. It's defined as a function, which is what the def keyword mentions, and it takes parameters of input, output, and session. So input contains all of your inputs, output contains all of your outputs, and session you can just ignore. And then there is the app UI, which is a variable which contains the user interface specification of your program. So that is how it looks and all of the inputs and all of the outputs and where they're placed within the application. And then finally, you just give Shiny your app UI and your server, and you call it with that app that we imported from the library, and then it runs it. So here's just another flow chart to kind of visualize how Shiny works under the hood. So app is the fundamental coordinator between the app UI and the server. So the app UI will contain all of the definitions of the inputs, and it will send that to the app, which will then look at the server, and it'll check to see if any of the outputs are invalidated. So if any of the inputs have changed and need to be recalculated. When it does that, it'll tell the server that it needs specific outputs, which the server will then render and give back to the app. And the app will then hand those outputs back to the app UI so that it can be rendered. So for just a hypothetical example, no reason in particular, we'll just create a sample Shiny application that visualizes a PDB file as a 3D molecule. So to do this, we are going to use py3dmol for the visualization, and we will source our virtual environment and then just install that library using pip. So on the right-hand side of the screen, it might be a little small, but that's pretty much the actual code of this application as we start building it. And then the bottom right-hand corner, once the application is actually able to run, will show you what it currently looks like. So first thing we need to do is actually configure the UI. So that app UI that we pass to the server is a hierarchy of UI elements that starts with a page, and then the page consists of a bunch of layouts, and the layouts consist of a bunch of elements, which are like inputs and outputs. So Shiny has a lot of documentation, and there's a bunch of these, so I won't get into too much detail here, but we'll just choose a page fluid for our application. This pretty much just tells Shiny that take the width of the browser and do whatever you want so that it looks nice with the rendering. So this works really well for mobile and desktop. Within this page fluid, we will have a layout for a sidebar layout. So this just has a sidebar on the left and then your content on the right. Within the sidebar, we will just define a simple input text, which, as you may have guessed, is a text field that users can input text into that we will call PDB ID, where the user can put in the ID the ID that they want to render, and then that'll get passed on to the server. There are three important things to note when you're creating an input or an output. There is the ID field, which is kind of confusing because I called it PDB ID, but this is a separate thing. So the ID is the identifier of this particular input or output and is what you will use to reference to it on the server. Then there is a value, which is just the default value you want to set it as, and then a label, which is what will be shown above this input on the UI. All of these elements are contained within the UI namespace of the Shiny library. So we need to modify our import statement to include UI, and then we just reference it by doing UI.pageFluid, UI.layoutSidebar, whatever. And then you can see in the bottom right, we have a very simple application right now that doesn't do anything, but it's progress. The next thing is that we actually need to configure the server. So the first thing we're going to want to do is create our model output. So Shiny has a lot of different types of outputs. So it can handle plots, it can handle images, it can handle data frames. It does all of that for you. But Py3D just the only way we can render this is through raw HTML. So we're just going to use the generic output.ui. Within that output.ui, we also need to specify an ID. Everything needs an ID that's input or output. And we specify that as model. Then within the server, we define a function with the exact same name model. So then when Shiny needs this output, it will call that model function and it will expect HTML to be returned. Within this, we just created a very basic placeholder that just sends a HTML bolded string that contains the PDB ID. And to do that, all we needed to do is call that input variable that's passed to the server, and then we just put the ID of the ID that we're looking for, which in this case is just ID, and then we get that value and we can output it back to the UI. As I mentioned before, the reactivity of Shiny means that it automatically noticed that we used the PDB ID within model and it connected the two. So if you change ID now, so instead of 1UPP, we just change it to 1UPQ, then Shiny will automatically invalidate that output and it will update it so that it's displayed on the HTML. So there's two more small things that we need to add to this function. These are called decorators, which you don't really need to understand how they work. All you need to know is that they pretty much just inform Shiny what this function does in particular. So the first thing we add is we tell it that it is an output. So it knows that this function will return some sort of output. And the second is that we need to specify what kind of output that is. In this case, since we're using an output UI, we just say that it's a render.ui. And this render is another namespace that we need to import from Shiny. So we update that accordingly. And then you can see in the bottom right-hand corner that the PDB ID is being rendered in bold, which is very nice. Finally, we just add our Py3D mol specific logic. So Py3D mol is a pretty simple library to use. We just import the view object from the library, and then we create the view and we pass it the ID that we gotten from our input. We mess around with some of the styling, and then we write the HTML version of that model, and we send that back to the application, which will then handle the rendering, as you can see here, very pretty. Finally, we just want to add a download button so that the user can download this HTML and view it on their own computers whenever they want. So to do this, it's quite simple. We just use the download button UI, which again takes an ID, which in this case is just download. Then we create a function within the server that is got the same name, so in this case, download. And all we need to do is yield the HTML to the client, which is as simple as just yield HTML. Since both the model and the download generate the HTML, we just abstracted the HTML generation to its own generate function within the server. We don't put any decorators on this one because it's not actually for Shiny to use. It's for our own functions to use, which just generates the HTML given the current ID. And then the model just returns that as a Shiny HTML container so it can be rendered. And the download yields it so that the user can download it. So now we have actually, I'll just go back just to show the size of code on the right. So that's the entire program that renders the PDB. So as I had mentioned, Python is very concise. So you can do a lot and not a lot. Finally, we need to run the application. So as I had shown at the very beginning, you just run Shiny, run from your terminal as long as your virtual environment is activated, and it'll do all of the work that you need as long as app.py exists. So by default, it binds to port 8000, and it will only run on the local network. So if you want to run this for serving on the web, you'll probably want to change the port to something like 80 for HTTP or 443 for HTTPS. And you'll also want to add this host argument to specify 0000, which just tells Shiny to broadcast the application on every network, not just the local one, so that you can access it from the internet. Finally, WebAssembly. So as I mentioned, ShinyLive was also released at the same time as PyShiny, and it allows you to turn your Shiny application into a WebAssembly application. This is very nice because the performance is usually better. You can immediately upload files since you're not actually uploading the files to the server. You are just sending it to your browser, and you don't need a server because you can just use a static file host, and Shiny will download all of the files. It'll manage the dependencies, and it'll compile the application down into WebAssembly to be run locally on the browser. There are some downsides that need to be taken into consideration. The main one is just that some libraries are not supported, which I'll get into in the next slide. And there's also an initial loading time. So because the browser needs to download the application, it needs to grab all of the dependencies, it needs to compile down the application. So on a good internet speed, it takes about maybe like 5 to 15 seconds, depending on what libraries you're using. But assuming that we want to create a WebAssembly application, which for this one we do, it's as simple as installing the ShinyLive library from pip and then just running ShinyLive export source site, where source is the folder that contains your app.py and site is the folder that you want your WebAssembly site to be exported to. And that's all that you have to do. Once you have that, the site will have an index.html at its root, and you can either open the HTML on your website to see it, you can point your website to the index.html, or if you want to run it locally on your computer, you can use Python's HTTP server in the same way that we used the virtual environment, and just point it to the site, bind it to 0000 to broadcast to the whole network, and specify a port. So the library caveat with WebAssembly is an interesting one. So pretty much all of the libraries that you use in your application, if you want it to run in WebAssembly, have to be completely written in Python, or in the tech jargon term, it has to be a pure Python wheel. So the issue is that ShinyLive uses this thing called pyadide in the backend, which pretty much takes Python and it converts it to WebAssembly. So if you have a library that is written in components of C or C++, pyadide doesn't know how to interpret that and compile it down into WebAssembly and link it with the rest of the application. So it needs to be pure Python, which you can find pretty easily by just going to shinylive.io/pyexamples. You can import micropip at this little console that it'll give you, and you can try to install it normally. Some applications like NumPy and SciPy, which are quite popular and aren't written purely in Python, have explicit support added in, so you can test around even if you think that your library doesn't support it, and it might. For those libraries that are supported, though, you need to tell ShinyLive what those libraries are so it knows to download them on the initial loading stage. You just create a requirement text.file in the same folder as your app.py, and you list off the libraries line by line. So in our case, it would be py3dmol, and that would be it. And yeah, that is my presentation. Hope you learned something.
So much.